All right, part 2 of our quantum mechanics lecture, photon energy in the EM spectrum, right? So with photoelectric effect, we got to electromagnetic waves have energy quantized in units of HF. So E equals HF, or if you use the equation lambda F equals C, you can rearrange this as E equals hc over lambda by substituting in for the frequency. We often also use Planck's constant in its electron volt seconds form rather than joule seconds form because this puts it more on the level of things that we sort of think of when we're talking about individual photons interacting with matter. So, this would be one of those things, 10 to the minus fifth EV. 10 to the minus fifth EV. Let me pull up Excel, and we will we'll look at something real quick. So the frequency on your microwave is 2450 megahertz, so 2450 e to the sixth, right? And Planck's constant 4.14 times 10 to the minus fifth, 14 times 10 to the minus 15th electron volts seconds. HF is the energy in an individual photon, right? So Planck's constant times the frequency of your microwave gives us, look at that, gives us 1 times 10 to the minus fifth, or 1.01 times 10 to the minus fifth electron volts, which is the rotational frequency for water, right? So these photons are hitting the water molecules in your microwave and causing them to have lots of kinetic energy for a water molecule, right? And it all adds up to a lot of heat. Okay, so vibrational energies of molecules, 4 orders of magnitude higher. Energy between outer electron shells and atoms, about 1 eV. Binding energy of weakly bound molecule, about 1 eV. Energy of red light, about 2 eV. Binding energy of tightly bound molecule, 10 eV. And then energy to ionize an atom or a molecule, 10 to 100 eV. All right, so this is sort of the scale of things in electron volts. And this is a useful unit, since an electron volt is something like 1.6 times 10 to the minus 19 joules, right? So an electron volt is a lot smaller than a joule. And it makes it a useful energy when dealing with individual atoms and molecules. All right, so what does that look like across our spectrum? Right, here's frequencies. We've got visible light right here around 10 to the 15th. And here's your microwaves in here. All right, 4 times 10 to the minus fifth. And all of this, if you look at this, our visible spectrum around electron volt to 4 electron volts. All right. Ultraviolet gets us up into 41, X-rays up in the 4 kiloelectron volts, and then gamma as we start getting into the mega, and on up into the gamma GeV, giga electron volts, right? So, and then of course down here in radio waves we're like peep squeak power, not much power at all down here. So once we understood photons had energy, then we began to look at some other things. And one was you could hit an electron with a photon, all right? And the photon would bounce off, boom, boom, right? And the electron would take off in some other direction. Now, what does that mean? That means the electron has momentum right? And it turns out the momentum equals h over lambda. That's the momentum of a photon. All right, the energy is hc over lambda. The momentum is h over lambda, so the energy of a photon is pc. Yes, the energy of a photon is pc, politically correct energy. So energy of a photon is pc. That would be one way to say solar energy. Solar energy is what you should be using. Solar energy is pc, energy of a photon, pc. Then all of this speaks to photons, photon energy. It ties back to the photoelectric effect and individual photons, right? This spoke to individual photons because got to remember, before this we didn't know about photons. Before the photoelectric effect was really understood, we didn't know about photons. That leads to photons. It leads to us understanding them as individual packets of energy, leads to us thinking of the spectrum in terms of the energy of the photons, and leads to the discovery of these things actually have momentum and can interact with electrons and protons and neutrons for that matter, but not as well. So they can interact with all of these in such a way that we can measure the momentum of the photon. And when we measure the momentum of the photon, we get P equals h over lambda. All right, I think that's enough for part 2, and we'll finish up in part 3.